You found a moment of peace to join me on this cosmic journey. We're going to explore something so violent, so catastrophically powerful, that it makes our sun look like a flickering candle in comparison. Something that can outshine entire galaxies for weeks and forge the heaviest elements in the universe in mere seconds. What is the most powerful thing in the universe? If you find comfort in these gentle explorations of the cosmos, I'd be grateful if you'd consider subscribing and hitting that like button. These visuals are here for you, but there's absolutely no problem if you drift off midway through the video. Feel free to close your eyes, breathe deep, and let your imagination soar through the cosmos at the speed of wonder. I'd also love to know where you're listening from tonight. Drop your time and location in the comments below. Are you watching the stars emerge in your corner of the world? Perhaps it's morning where you are, with sunlight streaming through your window. Do let me know. Now, let's begin. You're standing in your backyard on a clear night, gazing up at the constellation Orion. That bright red star on his shoulder, Betelgeuse, is quietly preparing for one of the most spectacular shows the universe has to offer. Not tonight, not next year, but sometime in the next 100,000 years, that star will explode with such tremendous force that it will briefly outshine every other star in our galaxy combined. It will be visible during the day, casting shadows at midnight, and releasing more energy in 10 seconds than our sun will produce in its entire 10 billion year lifetime. But even that mind-bending explosion pales in comparison to what we're here to explore, because there's something even more powerful lurking in the cosmic darkness, something so energetic that it makes regular supernovas look gentle by comparison, something that represents the absolute pinnacle of stellar violence and cosmic fury. Welcome to the realm of hypernovas, the most powerful explosions in the universe since the Big Bang itself. These are not just bigger supernovas, they're fundamentally different beasts altogether, cosmic monsters that can release 100 times more energy than their already spectacular cousins. They're so powerful, they can be seen from billions of light years away, so energetic they can strip the ozone layer from planets hundreds of light years distant. So violent, they create the most extreme environments possible in our universe. We'll journey to the hearts of dying stars more massive than anything you can imagine. We'll witness the birth of black holes in real time. We'll explore how these cosmic cataclysms seed the universe with the heaviest elements, forge magnetic fields trillions of times stronger than Earth's, and launch jets of material at nearly the speed of light across thousands of light years of space. But here's what makes this story truly extraordinary. These hypernovas aren't just cosmic curiosities. They're the universe's way of recycling itself, of taking the ashes of the most massive stars and spreading them across the cosmos to become the building blocks of new worlds, new stars, and possibly new life. The gold in your jewelry, the platinum in your electronics, the uranium that powers nuclear reactors, all of it was forged in the unimaginable heat and pressure of these stellar death throes. As we embark on this journey together, prepare to have your sense of scale completely recalibrated. We'll explore explosions so powerful they can influence the evolution of entire galaxies, jets of material so energetic they punch holes through interstellar space, and magnetic fields so intense they would kill you from 1,000 miles away. Yet somehow, miraculously, these same violent processes are responsible for creating the very elements that make life possible. So settle in, take a deep breath, and prepare to witness the universe at its most extreme. Because we're not just talking about explosions, we're talking about cosmic events so powerful they reshape reality itself, so energetic They challenge our understanding of physics. So spectacular, they remind us just how small we are in this vast, violent, and utterly magnificent cosmos. The story begins not with an explosion, but with a star. Not just any star, but a monster. A stellar giant so massive that our sun would look like a grain of sand beside a basketball in comparison. These are the Wolf-Rayet stars, the O-type supergiants, the luminous blue variables, stars that burn so hot and so bright they consume their nuclear fuel at a prodigious rate, living fast and dying young in the cosmic scheme of things. Picture a star 50, 60, perhaps even 100 times more massive than our sun. Where our sun burns hydrogen at a leisurely pace that will sustain it for 10 billion years, these stellar behemoths race through their nuclear fuel like cosmic dragsters. They burn hydrogen, then helium, then carbon, neon, oxygen and silicon in successive shells, each fusion process happening faster and more violently than the last. But here's where the story takes a dramatic turn. Unlike smaller stars that can shed their outer layers gently or explode as regular supernovas, these stellar monsters face a different fate entirely. When they reach the final stages of their lives, when their cores have been converted to iron and can no longer sustain nuclear fusion, something extraordinary happens. The core doesn't just collapse, it collapses so violently, so completely, that it tears a hole in the fabric of space and time itself. In less than a second, a core with the mass of several suns collapses from the size of Earth to a point just 20 kilometers across. The density becomes so extreme that protons and electrons are crushed together to form neutrons. But sometimes, not even neutron degeneracy pressure can halt this collapse. The core keeps shrinking, past the point where light can escape, past the point where space and time have any meaning as we understand them. A black hole is born, not the gentle, gradual formation we might imagine, but a violent, catastrophic birth that announces itself to the universe with a roar of energy that can be detected from billions of light years away. The outer layers of the star, suddenly deprived of the support from their core, come crashing down at speeds approaching 10% the speed of light. But here's where hypernovas reveal their unique signature. Instead of exploding symmetrically in all directions, like a regular supernova, these stellar death throes are fundamentally different. They're rotating, fast. Some of these massive stars spin so rapidly that their equators are moving at significant fractions of the speed of light. When the core collapses and forms a black hole, this rotation becomes concentrated, creating one of the most extreme objects in the universe, a rapidly spinning black hole surrounded by a disk of incredibly hot, dense material. This is where the real show begins. The rotating black hole, through processes we're still trying to fully understand, launches jets of material from its poles at velocities that approach the speed of light itself. These aren't gentle streams of gas. These are cosmic blowtorches, beams of plasma and radiation so energetic they can punch through the entire star and keep going for thousands of light years beyond. When these jets break through the surface of the dying star, they create something unprecedented in the universe, a hypernova, an explosion so powerful it can outshine an entire galaxy, so energetic it can be detected from the edge of the observable universe, so violent it creates conditions more extreme than anything that has existed since the first moments after the Big Bang. The energy released in those first few seconds is almost incomprehensible. In just 10 seconds, a hypernova releases more energy than our sun will produce in its entire 10 billion year lifetime. That's more energy than a trillion nuclear weapons exploding every second for millions of years. It's enough energy to power human civilization for longer than the universe has existed, released in the time it takes you to count to 10. But raw energy is just the beginning of this cosmic story. Because hypernovas don't just release energy, they create. In the unimaginable heat and pressure of these explosions, nuclear fusion goes into overdrive. Elements that cannot be created anywhere else in the universe are forged in abundance. Gold, platinum, uranium, thorium, all the elements heavier than iron that make modern technology possible, are created in these stellar death throes. The temperatures in a hypernova's core reach billions of degrees. The pressures exceed anything we can recreate on Earth by factors of trillions. Under these extreme conditions, atomic nuclei are smashed together with such violence that they stick, creating heavier and heavier elements through processes called rapid neutron capture. In just a few seconds, a hypernova can create more gold than exists in our entire solar system. These newly forged elements don't just sit there. They're blasted out into space at tremendous velocities, seeding the interstellar medium with the heavy elements that will eventually become part of new stars, new planets, and perhaps new forms of life. The gold in your wedding ring, the silver in your electronics, the platinum in your car's catalytic converter. All of it was forged in the heart of a dying star and blasted across the cosmos by one of these incredible explosions. But hypernovas have another trick up their sleeve, something that makes them even more special than their already incredible energy output and element creation. They create gamma-ray bursts, the most energetic electromagnetic events known to occur in the universe. When those jets of material break through the star's surface, they create focused beams of gamma radiation so intense they can sterilize planets from hundreds of light years away. These gamma-ray bursts are like cosmic lighthouses, beacons of energy that can be seen from the very edge of the observable universe. They last anywhere from milliseconds to several minutes, but in that brief time, they can release more energy in gamma rays alone than our sun will produce in its entire lifetime. They're so bright that if one occurred in our galaxy and happened to be pointed in our direction, it could cause a mass extinction event on Earth, despite being thousands of light years away. The magnetic fields created in these explosions are equally mind-boggling. We're talking about magnetic fields trillions of times stronger than Earth's magnetic field, so intense that they would be lethal to any form of life from a distance of 1,000 miles. These magnetar strength fields help shape and focus the jets, creating the collimated beams that make hypernovas so distinctive and so dangerous. What makes these magnetic fields even more extraordinary is how they interact with the surrounding space. Imagine invisible lines of force so powerful they can twist and distort the very fabric of space-time around them. As the newly formed black hole spins, it drags these magnetic field lines along with it, creating a cosmic dynamo that generates electrical currents powerful enough to light up entire star systems. These currents don't flow through copper wires like the electricity in your home. They flow through plasma so hot that electrons have been stripped away from their atoms, creating a soup of charged particles that responds to magnetic fields like iron filings, responding to a magnet. But instead of gentle alignment, we're talking about plasma being accelerated to nearly the speed of light, creating particle beams that could vaporize planets from interstellar distances. The jets themselves are marvels of cosmic engineering that put our most advanced rocket engines to shame. These aren't the gentle solar wind that flows from our sun at a leisurely 1,000,000 miles per hour. These are relativistic jets, streams of matter and energy moving at 99% the speed of light or faster. At these velocities, the normal rules of physics begin to break down. Time dilation becomes extreme. Length contraction becomes significant. The kinetic energy of individual particles approaches infinity. Picture this if you can. A stream of plasma, wider than our solar system, moving at nearly the speed of light, punching through thousands of light years of space like a cosmic drill bit. The material in these jets is so energetic that a single particle could deliver more energy than a baseball traveling at 60 miles per hour. Now multiply that by the trillions upon trillions of particles in the jet, and you begin to understand the sheer scale of violence we're dealing with. But here's what truly sets hypernovas apart from every other cosmic phenomenon. They're not just explosions, they're creators and destroyers simultaneously, cosmic alchemists that transform the heaviest elements while obliterating everything in their path. When these jets interact with the interstellar medium, the thin gas that exists between stars, they create shockwaves that propagate for millions of years after the initial explosion. These shockwaves are like cosmic tsunamis, sweeping up interstellar dust and gas, compressing it, heating it, and triggering the formation of new stars. In a very real sense, hypernovas are stellar midwives. They're violent deaths giving birth to the next generation of stars. The heavy elements they scatter become incorporated into these new stellar nurseries, enriching them with the materials necessary to form rocky planets and, eventually, life as we know it. The temperatures generated in these explosions challenge our understanding of matter itself. We're talking about conditions where the distinction between matter and energy becomes meaningless, where particles are created and destroyed in microseconds, where the fundamental forces of nature are pushed to their absolute limits. At these temperatures, atomic nuclei move so fast they can overcome the electrical repulsion that normally keeps them apart, allowing fusion reactions that are impossible under any other circumstances in the universe. Consider the incredible precision required for these processes to work. The rotation rate of the progenitor star must be just right. Too slow, and you get a regular supernova. Too fast, and the star might tear itself apart before it can form a black hole. The mass must fall within a narrow range. Too light, and the core becomes a neutron star instead of a black hole. Too heavy, and the collapse might happen so quickly that no explosion occurs at all. Just a star that vanishes into a black hole without a trace. The magnetic field strength must be perfectly calibrated to focus the jets without dissipating them. The composition of the star's outer layers must be precisely balanced to allow the jets to break through, while still providing enough material to power the explosion. It's as if the universe has fine-tuned these stellar monsters to produce the most spectacular fireworks show possible, while simultaneously serving as cosmic foundries for the heaviest elements. But perhaps the most mind-bending aspect of hypernovas is their relationship with time itself. Due to the extreme gravitational fields present during the collapse, time dilation effects become significant. From the perspective of matter falling into the newly formed black hole, the collapse might seem to take forever, with time stretching toward infinity as it approaches the event horizon. But from our external perspective, the entire collapse and explosion unfolds in mere seconds. This creates a fascinating paradox. The material powering the jets, accelerated to nearly the speed of light by the black hole's rotation, experiences time very differently than we do. A journey that might take thousands of years in our reference frame could seem like minutes to a particle in the jet. It's as if these explosions exist partially outside our normal experience of time, operating according to the exotic physics of extreme gravity and relativistic motion. The aftermath of a hypernova is equally spectacular. Long after the initial explosion has faded, the jets continue to interact with the surrounding interstellar medium, creating expanding bubbles of hot gas that can remain visible for millions of years. These superbubbles, as astronomers call them, can grow to hundreds of light years across, creating cavities in space that influence the formation of new stars and the evolution of entire galactic regions. Within these expanding shells of hot gas, the heavy elements created in the explosion mix and cool, eventually condensing into dust grains that will become the building blocks of future planets. It's a cosmic recycling program on an unimaginable scale, where the death of one massive star provides the raw materials for countless new worlds. The energy from these explosions doesn't just dissipate into space, it heats the interstellar medium, drives turbulence in molecular clouds, and can even influence the rate of star formation across entire galaxies. In the most extreme cases, hypernovas might be powerful enough to affect the evolution of their host galaxies, creating feedback mechanisms that regulate the growth of galactic bulges and the formation of supermassive black holes. But here's something that might surprise you. Despite their incredible violence, hypernovas are relatively rare events. In a galaxy like our Milky Way, they might occur only once every few million years. This rarity makes them even more precious from a cosmic perspective. Each hypernova represents the death of one of the universe's most massive stars, events so uncommon that most galaxies might host only a handful throughout their entire histories. This scarcity also means that when they do occur, their effects are felt across vast regions of space. A single hypernova can influence star formation, element distribution, and galactic evolution across hundreds of millions of cubic light years. They're like cosmic punctuation marks, rare but profound events that shape the structure and composition of the universe around them. The detection of these events from Earth requires some of the most sensitive instruments ever built. The gamma ray bursts they produce can be detected by satellites orbiting our planet, but the afterglow in visible light often requires the largest ground-based telescopes to observe. When astronomers do detect a hypernova, it becomes a priority target for observatories around the world, as these events provide unique opportunities to study matter under the most extreme conditions possible. Each observation teaches us something new about the fundamental physics of our universe. How do magnetic fields behave under extreme conditions? What happens to matter when it's accelerated to nearly the speed of light? How do black holes form and begin spinning? These questions can only be answered by studying these cosmic extremes, making hypernovas natural laboratories for testing our understanding of physics at its limits. As we contemplate these cosmic monsters, it's worth remembering that we exist because of them. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was forged in the hearts of dying stars and scattered across the cosmos by explosions like these. We are quite literally made of stardust, the recycled remnants of ancient stellar explosions that occurred billions of years before our solar system even existed. In a very real sense, hypernovas are the universe's way of ensuring its own future. By creating and distributing heavy elements, they make possible the formation of rocky planets, complex chemistry, and ultimately, life itself. Without these violent stellar deaths, the universe would be a much simpler, emptier place, populated only by hydrogen and helium with no possibility for the rich complexity we see around us today. The story of hypernovas becomes even more extraordinary when we consider their role as cosmic timekeepers, marking the epochs of universal evolution with their brilliant signatures. Each one represents a chapter in the grand narrative of how our universe transformed from a simple soup of hydrogen and helium into the complex, element-rich cosmos we inhabit today. But to truly understand the power of these cosmic giants, we need to journey deeper into their mechanics, into the precise choreography of physics that makes them possible. Because hypernovas aren't just random explosions. They're the result of an intricate dance between gravity, rotation, magnetism, and nuclear physics, all operating at the absolute extremes of what the universe allows. Let's begin with the progenitor, stars themselves. These aren't your average stellar citizens. We're talking about stars so massive they challenge our ability to even conceptualize their scale. Imagine a star with the mass of 60 suns, but compressed into a radius only 10 times larger than our own sun. The gravitational forces at work here are almost incomprehensible. The surface gravity would be so intense that a grain of sand would weigh as much as a car on Earth. These stellar monsters live their lives in the fast lane, where our sun converts about 4 million tons of matter into energy every second. These giants burn through their nuclear fuel at rates that would make our sun look practically dormant. They're consuming hundreds of millions of tons of matter every second, converting it to energy through nuclear fusion processes so violent they create temperatures exceeding 100 million degrees in their cores. The pressure at the center of these stars is equally staggering. We're talking about pressures billions of times greater than anything at the center of Earth. Forces so intense they squeeze atomic nuclei together despite their natural electrical repulsion. Under these conditions, the normal rules of chemistry break down completely. Matter exists in states that have no equivalent anywhere else in the universe, except in the hearts of neutron stars and the event horizons of black holes. But here's where the story becomes truly fascinating. These massive stars don't just burn their fuel. They burn it in layers, like cosmic onions of nuclear fusion. The core burns hydrogen into helium. Surrounding that, a shell burns helium into carbon and oxygen. Above that, carbon burns into neon and magnesium. Higher still, neon burns into oxygen and silicon. And finally, in the outermost burning shell, silicon fuses into iron. Each layer burns at different rates, creating a complex structure that's constantly evolving, constantly shifting as the star races through its nuclear fuel. The temperatures and pressures required for each successive burning stage become more and more extreme. Silicon burning, the final fusion process that can release energy, requires temperatures exceeding 3 billion degrees. At these temperatures, photons themselves become so energetic they can create matter and antimatter pairs, adding another layer of complexity to the stellar interior. But iron represents the end of the road. Iron nuclei are the most stable in the universe. You can't extract energy by fusing iron into heavier elements, and you can't extract energy by breaking iron apart into lighter ones. When the core of a massive star becomes dominated by iron nuclear fusion stops, the star's energy source, the outward pressure that has been fighting gravity for millions of years, suddenly vanishes. What happens next occurs so quickly, it defies human comprehension. In less than a second, the iron core collapses from the size of Earth to a sphere barely 20 kilometers across. The density increases by a factor of trillions. Electrons are crushed into protons, forming neutrons and releasing ghostly particles called neutrinos that carry away enormous amounts of energy. But in the most massive stars, the ones destined to become hypernovas, even neutron degeneracy pressure cannot halt the collapse. The core is simply too massive, too compressed, too overwhelmed by its own gravity. It continues to collapse past the neutron star stage, past the point where light can escape, into the realm of black holes. The formation of a black hole is itself a process that challenges our understanding of physics. As matter crosses the event horizon, it enters a region of space-time so warped that the normal concepts of space and time break down. From our external perspective, this happens almost instantaneously. But the process creates gravitational waves, ripples in space-time itself that propagate outward at the speed of light, carrying information about this cosmic catastrophe to detectors here on Earth. Now comes the truly spectacular part. The newly formed black hole inherits the angular momentum of the collapsing core. If the progenitor star was rotating rapidly, and most massive stars do rotate due to their formation process, this angular momentum becomes concentrated into an incredibly small volume. The result is a black hole spinning at tremendous rates, perhaps hundreds of times per second. This rotation is crucial to the hypernova process. A spinning black hole is fundamentally different from a static one. It drags space-time around with it, creating a region called the ergosphere, where space-time itself is forced to rotate. Within this region, the distinction between space and time becomes blurred, and energy can be extracted from the black hole's rotation through processes that seem to violate our everyday understanding of conservation laws. The mechanism that creates the hypernova jets involves the interaction between the black hole's rotation, its powerful magnetic field, and the disk of material spiraling into it. As matter falls toward the black hole, it forms an accretion disk, a swirling maelstrom of superheated plasma that glows with the intensity of millions of suns. The magnetic field lines threading this disk become twisted and amplified by the black hole's rotation, creating a cosmic dynamo of unimaginable power. These twisted magnetic field lines act like cosmic particle accelerators, channeling material from the accretion disk into narrow jets that shoot out from the black hole's poles. The particles in these jets are accelerated to velocities approaching the speed of light, carrying away tremendous amounts of energy and angular momentum from the system. But here's what makes hypernovas truly unique among cosmic explosions. The jets don't just carry away energy, they carry away information in the form of gravitational waves, neutrinos, and electromagnetic radiation across the entire spectrum. This multi-messenger signature allows astronomers to study these events using completely different types of detectors, from gravitational wave observatories to neutrino telescopes to gamma-ray satellites. The neutrinos produced in hypernova explosions are particularly fascinating. These ghostly particles barely interact with matter, allowing them to escape from the explosion's core and travel across the universe virtually unimpeded. A single hypernova can produce more neutrinos in 10 seconds than our Sun will produce in its entire lifetime. These neutrinos carry information about the explosion's core, about the nuclear processes occurring under conditions more extreme than anything we can recreate in laboratories. When astronomers detect a hypernova, they're not just seeing an explosion, they're witnessing the birth of a black hole, the creation of elements heavier than iron, the generation of magnetic fields stronger than anything else in the universe, and the acceleration of matter to relativistic speeds. It's like watching the universe's most extreme physics experiment unfold in real time. The jets themselves create their own remarkable phenomena as they interact with the surrounding stellar material. As they punch through the star's outer layers, they create shockwaves that heat the material to billions of degrees, causing it to emit X-rays and gamma rays. The interaction between the jets and the stellar envelope creates complex hydrodynamic instabilities, turbulence patterns that mix the newly created heavy elements throughout the explosion. These mixing processes are crucial for distributing the hypernova's chemical products throughout space. Without efficient mixing, the heavy elements created in the explosion's core might remain locked away, unable to enrich the interstellar medium. But the violent turbulence created by the jets ensures that gold, platinum, uranium, and other heavy elements are thoroughly mixed with the lighter elements in the star's outer layers and blasted into space. The energy distribution in a hypernova is equally remarkable. While regular supernovas release most of their energy in the form of kinetic energy of the expanding debris, hypernovas channel a significant fraction of their energy into the jets. This creates a highly directional explosion, with most of the energy focused into narrow cones along the rotation axis. This directionality has profound implications for both the explosion's immediate effects and its long-term impact on the surrounding environment. Material in the equatorial plane might experience a relatively gentle explosion, while regions along the polar axis are subjected to the full fury of the relativistic jets. This creates an asymmetric distribution of heavy elements in the surrounding space, influencing the composition of future generations of stars and planets. The magnetic fields generated in these explosions deserve special attention. We're talking about field strengths that exceed Earth's magnetic field by factors of trillions. These magnetar strength fields are so intense they would disrupt atomic structure from thousands of miles away. They're strong enough to bend light, to twist space-time, to create conditions where the normal laws of electromagnetism break down. These extreme magnetic fields don't just disappear after the explosion. They become frozen into the expanding debris, creating magnetized shells of material that can persist for thousands of years. As these shells expand and interact with the interstellar medium, they can trigger the formation of new stars, influence the structure of molecular clouds, and even affect the magnetic field of the entire galactic region. The interaction between hypernova remnants and the interstellar medium creates some of the most beautiful and complex structures in the universe. The expanding shock waves carve out vast cavities in space, creating bubbles of hot, tenuous gas that can be hundreds of light years across. These superbubbles become nurseries for new stars, their walls compressed and enriched with heavy elements from the original explosion. Within these expanding shells, the physics becomes incredibly complex. We're dealing with magnetohydrodynamics under extreme conditions, where magnetic fields, fluid dynamics, and plasma physics all interact in ways that challenge our most sophisticated computer models. The turbulence created by these interactions can persist for millions of years, constantly mixing and redistributing the explosion's products throughout the local galactic environment. But perhaps the most remarkable aspect of hypernovas is their role in cosmic evolution. These explosions don't just create heavy elements, they regulate the rate at which stars form throughout the galaxy. The energy they inject into the interstellar medium can either trigger star formation by compressing molecular clouds or suppress it by heating the gas to temperatures where it cannot collapse under its own gravity. This regulatory mechanism helps explain why galaxies don't convert all their gas into stars immediately. The feedback from hypernovas and other stellar explosions creates a balance between star formation and gas heating, allowing galaxies to continue forming stars over billions of years rather than exhausting their fuel supplies in a single burst of activity. The heavy elements created in hypernovas also play a crucial role in planetary formation and the development of life. Rocky planets like Earth simply cannot form without sufficient quantities of elements heavier than hydrogen and helium. The silicon that makes up our planet's crust, the iron in our core, the carbon that forms the backbone of organic chemistry, all of these elements were forged in stellar cores and distributed by explosions like hypernovas. But the story doesn't end with element creation. The specific isotopes produced in hypernova explosions have their own fascinating tales to tell. Radioactive isotopes created in these explosions serve as cosmic clocks, allowing us to date meteorites and understand the timeline of our solar system's formation. Some of these isotopes have half-lives of millions of years, meaning they were still decaying when our solar system formed, providing heat sources that may have been crucial for early planetary differentiation. The rare earth elements produced in hypernovas have become essential for modern technology. The neodymium in powerful magnets, the europium that makes red phosphors in television screens, the gadolinium used in medical imaging. All of these elements were created in the extreme conditions of stellar explosions and are now integral parts of our technological civilization. As we contemplate these cosmic furnaces, it's worth considering their frequency and distribution throughout the universe. Hypernovas are rare events occurring perhaps once every few million years in a galaxy like our own. But across the observable universe, with its hundreds of billions of galaxies, hypernovas are occurring constantly, perhaps several times per second, somewhere in the cosmos. This rarity makes each hypernova precious from a scientific perspective. When astronomers detect one of these explosions, observatories around the world swing into action, coordinating observations across the electromagnetic spectrum to capture as much information as possible about these fleeting events. The data collected from a single hypernova can keep researchers busy for years, revealing new insights into stellar evolution, black hole formation, and the synthesis of heavy elements. The future of hypernova research is equally exciting. New generation telescopes and detectors will allow us to study these explosions in unprecedented detail. Gravitational wave detectors are becoming sensitive enough to detect the space-time ripples produced by black hole formation. Neutrino telescopes buried deep underground or in Antarctic ice are beginning to catch the ghostly particles that escape from explosion cores. Multi-messenger astronomy, combining information from gravitational waves, neutrinos, and electromagnetic radiation, is opening new windows into the physics of these extreme events. Perhaps most intriguingly, hypernovas may serve as probes of fundamental physics under conditions we can never recreate in laboratories. The extreme densities, magnetic fields, and energies present in these explosions allow us to test our theories of gravity, nuclear physics, and particle physics at their limits. Each hypernova observation is like conducting a physics experiment with energies trillions of times greater than anything achievable in particle accelerators. The jets produced by hypernovas also serve as natural laboratories for studying relativistic plasma physics. The conditions in these jets, with matter moving at 99% the speed of light in magnetic fields stronger than anything we can produce, provide unique opportunities to test our understanding of how matter behaves under extreme relativistic conditions. As we continue to unravel the mysteries of hypernovas, we're also beginning to understand their role in the broader context of cosmic evolution. These explosions may have been crucial in the early universe, when the first generation of massive stars exploded and began the process of chemical enrichment that would eventually make planets and life possible. The connection between hypernovas and life itself is profound and humbling. Every breath you take contains oxygen atoms forged in stellar cores. Every heartbeat is powered by calcium ions created in stellar explosions. The iron in your blood, the phosphorus in your DNA, the sulfur in your proteins, all of it traces back to the violent deaths of massive stars billions of years ago. In this sense, we are not just observers of these cosmic phenomena, we are participants in the story they tell, temporary arrangements of stardust that have somehow learned to contemplate our own origins. The universe has evolved from simple hydrogen and helium into something complex enough to study itself, and hypernovas have played a crucial role in that remarkable transformation. The sheer scale of destruction that hypernovas can unleash extends far beyond their immediate vicinity. When one of these cosmic monsters detonates, it doesn't just affect the space around the dying star. The gamma-ray burst it produces can sterilize planets hundreds of light years away, stripping away protective ozone layers and bathing entire worlds in lethal radiation. It's a sobering reminder that in our universe, violence on one scale can have consequences that ripple across vast distances and eons of time. But here's something that might surprise you. Despite their incredible destructive power, hypernovas may actually be essential for life as we know it. The heavy elements they create and scatter throughout space don't just enable the formation of rocky planets. They make possible the complex chemistry that underlies biology itself. Without the carbon forged in stellar cores, there would be no organic molecules. Without the phosphorus created in these explosions, there would be no DNA or RNA. Without the sulfur blasted into space by dying stars, there would be no proteins. Consider the incredible journey that brought these elements to you. Billions of years ago, a massive star somewhere in our galactic neighborhood was racing through its nuclear fuel, burning ever heavier elements in its core. As it approached the end of its life, the star began to rotate faster and faster, like a figure skater pulling in her arms. The magnetic fields threading through its interior became twisted and amplified, setting the stage for one of the most violent events the universe can produce. When that ancient star finally collapsed, it created a black hole in a matter of seconds. The jets that erupted from its poles carved through the stellar envelope at nearly the speed of light, creating a fireball visible from billions of light years away. In those brief moments of ultimate violence, elements that had never existed before were forged in the unimaginable heat and pressure. Gold atoms were born. Platinum nuclei came into being. Uranium isotopes were created that would remain radioactive for billions of years. The explosion scattered these newly minted elements across hundreds of light years of space, where they mixed with the interstellar medium and eventually became incorporated into new generations of stars and planets. Some of those atoms, forged in that ancient stellar death, eventually found their way into the molecular cloud that would collapse to form our solar system. They became part of the rocky debris that coalesced into Earth. And ultimately, through the intricate processes of geology and biology, they became part of you. The gold wedding ring on your finger contains atoms that were forged in one of these cosmic furnaces. The platinum in your car's exhaust system was created in temperatures exceeding 10 billion degrees. The uranium powering nuclear reactors around the world was born in the heart of a dying star, in conditions so extreme they challenge our understanding of physics itself. But hypernovas don't just create elements, they create time itself, in a sense. The radioactive isotopes produced in these explosions serve as cosmic clocks, ticking away the eons and providing us with ways to measure the age of meteorites, the timing of stellar explosions, and the chemical evolution of our galaxy. Some of these isotopes have half-lives measured in millions of years, meaning they were still actively decaying when our solar system formed 4.5 billion years ago. The heat produced by these radioactive isotopes may have been crucial for the early evolution of planets like Earth. As uranium, thorium, and other radioactive elements decayed in our planet's interior, they provided the energy needed to drive plate tectonics, maintain a magnetic field, and keep our world geologically active. Without this internal heat source, Earth might have become a cold, dead world like Mars, unable to maintain the dynamic processes that make life possible. The magnetic fields generated in hypernova explosions deserve special attention because they represent some of the most extreme conditions possible in our universe. We're talking about field strengths that would be instantly lethal to any form of life from distances of thousands of miles. These magnetar strength fields are so intense, they can alter the quantum vacuum itself, creating virtual particles from empty space and bending light rays like gravitational lenses. Imagine trying to comprehend a magnetic field 1,000,000,000,000 times stronger than Earth's. At these intensities, the normal rules of atomic physics break down. Electrons are forced into highly elongated orbits. Atoms themselves become distorted into needle-like shapes. The very structure of matter is warped by the overwhelming magnetic forces. These extreme magnetic fields don't just disappear after the explosion. They become frozen into the expanding debris, creating magnetized shells of material that persist for thousands of years. As these shells expand through space, they interact with the galactic magnetic field, creating complex structures that can influence star formation across entire spiral arms. The study of these magnetic phenomena has opened entirely new fields of astrophysics. Magnetohydrodynamics, the study of how magnetic fields interact with conducting fluids like plasma, has become crucial for understanding everything from stellar interiors to galactic evolution. The extreme conditions in hypernova explosions provide natural laboratories for testing theories that cannot be verified anywhere else. But perhaps the most remarkable aspect of hypernovas is their role as cosmic sculptors, shaping the structure of galaxies themselves. When these explosions occur, they don't just release energy locally. They drive superbubbles of hot gas that can expand for millions of years, creating cavities in the interstellar medium that influence the formation of new stars across vast regions of space. These superbubbles can grow to hundreds of light years in diameter, creating low-density regions where star formation is suppressed and high-density walls where new stellar nurseries can form. The energy injected by hypernova explosions helps regulate the rate at which galaxies convert their gas into stars, preventing them from exhausting their fuel supplies too quickly and allowing star formation to continue for billions of years. The impact extends even further. In the most extreme cases, hypernovas may actually influence the evolution of their host galaxies' central black holes. The energy and angular momentum they inject into the galactic environment can affect how gas flows toward the galactic center, potentially regulating the growth of supermassive black holes and the formation of galactic bulges. This creates a fascinating feedback loop in galactic evolution. Massive stars form from gas in the galactic disk. They live brief, violent lives before exploding as hypernovas. These explosions enrich the interstellar medium with heavy elements, regulate star formation rates, and influence the galaxy's overall structure. The process then repeats with new generations of stars, each slightly more metal-rich than the last. Over billions of years, this cycle has transformed our galaxy from a simple collection of hydrogen and helium into the complex, chemically diverse environment we observe today. The Milky Way's spiral structure, its stellar populations, its distribution of heavy elements, all of these features have been shaped by countless stellar explosions stretching back to the galaxy's earliest epochs. The detection and study of hypernovas has revolutionized our understanding of stellar evolution and galactic chemistry. When astronomers first began detecting gamma-ray bursts in the 1960s, they had no idea what could produce such enormous amounts of energy in such brief periods. The mystery deepened when it became clear that these bursts were coming from cosmological distances, implying energy releases that seemed to violate known physics. The breakthrough came with the realization that gamma-ray bursts were highly directional, focusing their energy into narrow jets rather than radiating it uniformly in all directions. This solved the energy problem and revealed hypernovas as the most likely source of these mysterious signals. Suddenly, astronomers had a new tool for studying the most massive stars in the universe and probing conditions in the early cosmos. Modern hypernova observations involve a complex choreography of ground-based and space-based telescopes, When a gamma-ray satellite detects a burst, it immediately sends alerts to observatories around the world. Robotic telescopes swing into action within seconds, searching for the optical afterglow that follows the initial gamma-ray emission. Larger telescopes join the effort, studying the explosion's spectrum and measuring its distance and properties. These rapid response observations have revealed the incredible diversity of hypernova explosions. Some are highly energetic, releasing 100 times more energy than typical supernovas. Others are more modest, barely exceeding the energy output of their conventional cousins. Some produce jets that are clearly visible from our perspective. Others are viewed from angles that hide their jets, making them appear more like ordinary stellar explosions. The diversity extends to the progenitor stars themselves. While all hypernovas involve very massive stars, the exact mass range, rotation rates, and magnetic field strengths that lead to jet formation are still being determined. Some hypernovas may involve stars with masses exceeding 100 times that of our Sun. Others might require more modest masses, but extremely rapid rotation rates. The chemical signatures of hypernova explosions are equally varied. Some produce large quantities of nickel-56, the radioactive isotope that powers supernova light curves. Others create unusual ratios of heavier elements, suggesting different nuclear burning processes in their cores. The most exotic hypernovas might produce elements that are extremely rare in the universe, isotopes that can only be created under the most extreme conditions. These chemical fingerprints provide crucial clues about the explosion mechanism and the properties of the progenitor star. By studying the spectra of hypernova light, astronomers can infer the temperature, density, and composition of the exploding material. They can determine how much energy was released, how fast the debris is moving, and what elements were created in the explosion. The study of hypernova remnants has revealed equally fascinating details about these cosmic explosions. Years or decades after the initial outburst, the expanding debris continues to interact with the surrounding interstellar medium, creating complex shock structures that emit radiation across the electromagnetic spectrum. These remnants serve as long-term laboratories for studying the explosion's effects and the physics of shock waves in low-density environments. Some hypernova remnants show clear evidence of jet structure, with elongated morphologies that reflect the directional nature of the original explosion. Others appear more spherical, suggesting that the jets were either weak or that we're viewing the remnant from an angle that hides the jet signatures. The diversity of remnant shapes provides additional constraints on hypernova models and helps astronomers understand the three-dimensional structure of these explosions. The neutron stars and black holes left behind by hypernovas are equally remarkable objects. The black holes formed in these explosions are often rapidly rotating, with spins that can approach the theoretical maximum allowed by general relativity. These spinning black holes continue to influence their surroundings long after the initial explosion, powering jets and outflows that can persist for years or decades. Some hypernova black holes become the engines of quasars and other active galactic nuclei, continuing to convert matter into energy and launch jets across thousands of light years. The connection between hypernovas and these exotic objects provides another link in the chain of cosmic evolution, showing how stellar death can lead to some of the most energetic phenomena in the universe. The gravitational waves produced by hypernova explosions represent an entirely new way of studying these events. As the stellar core collapses and forms a black hole, it creates ripples in space-time that propagate outward at the speed of light. These gravitational waves carry information about the collapse process that cannot be obtained through electromagnetic observations alone. Future gravitational wave detectors may be sensitive enough to detect individual hypernova explosions from across the observable universe. This would provide unprecedented insights into the dynamics of stellar collapse, the formation of black holes, and the launch of relativistic jets. The combination of gravitational wave and electromagnetic observations promises to revolutionize our understanding of these cosmic extremes. The neutrinos produced in hypernova explosions offer yet another window into these events. These ghostly particles barely interact with matter, allowing them to escape from the explosion's core and carry information about conditions deep inside the dying star. While neutrinos from hypernova explosions are extremely difficult to detect, future neutrino telescopes may be able to catch these messengers from stellar death. The multi-messenger approach to hypernova astronomy, combining gravitational waves, neutrinos, and electromagnetic radiation, represents the future of extreme astrophysics. Each type of signal provides complementary information about different aspects of the explosion, creating a more complete picture than any single observational technique could provide. As we continue to study these cosmic monsters, we're also beginning to understand their role in the broader context of universe evolution. The first generation of stars, formed from pristine hydrogen and helium in the early universe, were likely more massive on average than the stars we see today. Many of these primordial giants may have ended their lives as hypernovas, beginning the process of chemical enrichment that would eventually make planets and life possible. The heavy elements created in these early explosions became incorporated into the next generation of stars, slightly changing their properties and evolution. Over billions of years, this process has gradually increased the metallicity of the universe, creating the conditions necessary for rocky planet formation and complex chemistry. The implications extend beyond our own cosmic neighborhood. Hypernovas may have played crucial roles in the evolution of the first galaxies, regulating star formation and black hole growth in the early universe. The energy they injected into the intergalactic medium may have helped heat and ionize the gas between galaxies, contributing to the reionization epoch that transformed the universe from opaque to transparent. These connections between stellar explosions and cosmic evolution highlight the interconnected nature of astrophysical processes. Nothing in the universe exists in isolation. The death of a single massive star can influence the formation of new stars across an entire galactic region. The heavy elements created in that explosion can become incorporated into planets orbiting stars that won't form for billions of years. This cosmic recycling program has been operating for nearly the entire history of the universe, gradually building up the inventory of heavy elements that make complex chemistry possible. Each generation of stars has been slightly more metal-rich than the last, creating a steady progression toward the conditions necessary for life. The story becomes even more remarkable when we consider the precise timing required for this process to work. Stars must live long enough to create heavy elements in their cores, but not so long that the universe expands and cools before they can explode. The explosion must be violent enough to scatter these elements throughout space, but not so energetic that it sterilizes entire galactic regions. The heavy elements must then be incorporated into new stars and planets at just the right rate to allow complexity to emerge. The fact that this delicate balance has been maintained for billions of years seems almost miraculous. Yet it's the natural result of the physical laws that govern stellar evolution, nuclear physics, and galactic dynamics. The universe appears to be finely tuned for the production and distribution of heavy elements, creating conditions that inevitably lead to chemical complexity and, potentially, life. As we contemplate these cosmic furnaces from our small rocky planet, it's worth remembering that we are not separate from this story. We are part of it. The atoms in our bodies were forged in stellar cores and scattered by explosions like hypernovas. We are temporary arrangements of stardust that have somehow learned to contemplate our own origins. This perspective transforms our understanding of what it means to be human. We are not isolated biological systems clinging to a small planet in an indifferent universe. We are expressions of the universe itself, complex patterns that have emerged from billions of years of cosmic evolution. The same physical laws that govern hypernova explosions also govern the chemistry of life, the formation of planets, and the evolution of consciousness. In studying hypernovas, we are really studying ourselves, tracing our origins back to the most violent events the universe can produce. These explosions created the elements that make our existence possible. They regulated the star formation processes that led to our solar system. They enriched the interstellar medium with the materials necessary for rocky planet formation. The connection runs even deeper. The energy that powers our civilization ultimately traces back to nuclear fusion, the same process that powers stars and creates heavy elements in hypernova explosions. The fossil fuels we burn were formed from organic matter that incorporated carbon created in stellar cores. The nuclear reactors that generate electricity use uranium forged in stellar explosions billions of years ago. Even our understanding of these cosmic phenomena depends on the heavy elements created in stellar explosions. The silicon in our computer chips, the rare earth elements in our electronics, the metals in our telescopes and detectors, all of these materials were created in the hearts of dying stars and distributed by explosions like hypernovas. This creates a beautiful symmetry in the universe. Stars create the elements necessary for planets, life, and intelligence. Intelligence develops the tools necessary to study stars. Through this process, the universe becomes aware of itself, using the products of stellar evolution to understand stellar evolution. The study of hypernovas thus represents more than just an investigation of extreme astrophysical phenomena. It's a journey of self-discovery, an exploration of our own cosmic heritage. In understanding these explosions, we understand something fundamental about our place in the universe and our connection to the cosmos that created us. As we continue to probe deeper into the mysteries of these cosmic monsters, we're not just satisfying scientific curiosity. We're uncovering the story of how simple hydrogen and helium were transformed into the rich, complex universe we inhabit today. We're tracing the origins of the elements that make life possible and understanding the processes that shaped our galactic environment. The journey from the first stars to the emergence of consciousness represents one of the most remarkable transformations in the history of the universe. Hypernovas have played a crucial role in this cosmic evolution, serving as the violent engines that created complexity from simplicity and made possible the emergence of intelligence from inanimate matter. In the quiet moments between these cosmic explosions, as we sit on our small planet orbiting an ordinary star, we can marvel at the chain of events that brought us into being. Every breath we take, every thought we think, every word we speak is connected to the violent deaths of massive stars that occurred billions of years before Earth even existed. The story of hypernovas is ultimately the story of us, written in the language of nuclear physics and played out on the stage of cosmic evolution. As we continue to study these magnificent explosions, we're really studying the processes that made our existence possible, tracing our lineage back to the most powerful events the universe has known since the Big Bang itself. And here we encounter one of the most profound mysteries in all of astrophysics. The question that has puzzled scientists for decades and continues to challenge our understanding of the most extreme physics imaginable. How do these relativistic jets maintain their coherence across thousands of light years of space? How do streams of plasma, moving at 99% the speed of light, remain focused and directed rather than dispersing into the cosmic void? The answer lies in the intricate dance between magnetic fields and rotation that occurs during the hypernova explosion. As the newly formed black hole spins, it drags the surrounding space-time along with it, creating what physicists call frame dragging. This rotation of space-time itself becomes a cosmic engine, extracting energy from the black hole's spin and channeling it into the jets through processes that seem to violate our everyday understanding of energy conservation. Picture this if you can. The magnetic field lines threading through the accretion disk become twisted like cosmic DNA helixes, wound tighter and tighter by the black hole's rotation. These twisted field lines act like invisible rails, guiding charged particles along precise trajectories and accelerating them to velocities that approach the ultimate speed limit of the universe. The magnetic pressure becomes so intense that it can overcome even the tremendous gravitational pull of the black hole itself. But here's where the physics becomes truly exotic. At the velocities achieved in these jets, the normal rules of space and time begin to break down. Length contraction becomes extreme, compressing the jet material into thin sheets. Time dilation stretches seconds into hours from the perspective of the accelerated particles. The kinetic energy of individual atoms approaches infinity, creating conditions that exist nowhere else in the universe, except perhaps in the first moments after the Big Bang. The particles in these jets aren't just moving fast. They're moving so fast that they begin to exhibit properties more commonly associated with high-energy physics experiments than with astronomical objects. Individual protons carry energies equivalent to cosmic ray particles that have been accelerated across billions of light-years of space. Electrons radiate away their energy so rapidly that they must be constantly re-accelerated to maintain their velocities. This constant acceleration creates a phenomenon known as synchrotron radiation, where charged particles spiraling in magnetic fields emit light across the entire electromagnetic spectrum. The intensity of this radiation is so extreme that it outshines entire galaxies, creating beacons that can be detected from the edge of the observable universe. The polarization of this light carries information about the magnetic field structure, allowing astronomers to map the invisible forces that shape these cosmic jets. But the jets themselves are just the beginning of the hypernova story. As they punch through the stellar envelope and emerge into interstellar space, they create shock waves that propagate at thousands of kilometers per second. These shocks heat the surrounding gas to temperatures exceeding 100 million degrees, creating expanding bubbles of X-ray emitting plasma that can remain visible for thousands of years after the initial explosion. The interaction between these shock waves and the interstellar medium creates some of the most complex and beautiful structures in the universe. Instabilities develop at the boundaries between hot and cold gas, creating turbulent mixing regions where the explosion's products are thoroughly stirred with the surrounding material. These mixing processes are crucial for distributing heavy elements throughout space and ensuring that future generations of stars will have access to the materials necessary for rocky planet formation. Consider the incredible precision required for these processes to work effectively. The shockwave velocity must be just right to heat the gas without blowing it away completely. The magnetic field strength must be perfectly balanced to channel the jets without allowing them to dissipate. The density of the surrounding medium must fall within a narrow range that allows efficient energy transfer without absorbing all the explosion's products. The temperatures generated in these shock-heated regions challenge our understanding of matter under extreme conditions. At 100 million degrees, atomic nuclei move so fast that they can overcome the electrical forces that normally keep them apart. Nuclear reactions that are impossible under normal stellar conditions become commonplace. Exotic isotopes are created and destroyed in microseconds. The boundary between matter and energy becomes increasingly meaningless. These extreme temperatures also drive processes that have no equivalent anywhere else in the universe. Pair production becomes efficient, with high-energy photons spontaneously creating electrons and positrons from the vacuum. Neutrino emission becomes so intense that these ghostly particles carry away significant amounts of energy, cooling the shocked gas and allowing it to radiate its energy into space. The interplay between these processes creates a complex web of energy transfer that astronomers are still trying to fully understand. The heavy elements created in hypernova explosions don't just enrich the local environment. They become incorporated into dust grains that serve as the building blocks for future planetary systems. These microscopic specks of stardust contain the concentrated essence of stellar death, carrying within their crystalline structures the nuclear signatures of the most violent events in the universe. When these dust grains eventually become part of new stellar systems, they bring with them the chemical complexity necessary for life as we know it. The silicon that forms the backbone of rocky planets, the iron that creates planetary magnetic fields, the carbon that enables organic chemistry. All of these elements were forged in the hearts of dying stars and dispersed by explosions that dwarf human comprehension. But hypernovas don't just create elements. They create isotopes, specific versions of elements with different numbers of neutrons in their nuclei. Some of these isotopes are stable, remaining unchanged for billions of years. Others are radioactive, decaying over timescales that range from seconds to billions of years. These radioactive isotopes serve as cosmic clocks, allowing scientists to date meteorites, understand the timeline of solar system formation, and trace the chemical evolution of our galaxy. The isotopic signatures of hypernova explosions are like fingerprints, unique patterns that reveal the conditions present during the explosion. By studying these signatures in meteorites and interstellar dust, astronomers can reconstruct the history of stellar explosions in our galactic neighborhood. They can determine when specific hypernovas occurred, how energetic they were, and what elements they contributed to the local interstellar medium. This isotopic archaeology has revealed a fascinating picture of our galaxy's violent past. The solar system appears to have formed in a region that had been enriched by multiple generations of stellar explosions, including several hypernovas that occurred in the billion years before the Sun's birth. The heavy elements in our bodies carry the signatures of these ancient explosions, connecting us directly to events that occurred long before Earth existed. The magnetic fields generated in hypernova explosions have their own remarkable properties that distinguish them from any other magnetic phenomena in the universe. These fields are not only incredibly strong, but they're also highly structured, with complex geometries that reflect the turbulent conditions present during the explosion. Field lines become twisted, braided, and reconnected in patterns that would be impossible to recreate in any terrestrial laboratory. The strength of these magnetic fields approaches the theoretical limits allowed by quantum mechanics. At these intensities, the magnetic field energy density exceeds the mass energy density of ordinary matter. Virtual particles are pulled from the quantum vacuum and given real existence. The normal laws of electromagnetism begin to break down, replaced by the exotic physics of quantum electrodynamics in strong field regimes. These ultra-strong magnetic fields don't dissipate quickly. They become frozen into the expanding debris of the explosion, creating magnetized shells that can persist for thousands of years. As these shells expand through space, they sweep up interstellar material and amplify the galactic magnetic field. Over millions of years, the cumulative effect of many hypernova explosions helps maintain and structure the magnetic field that permeates our entire galaxy. The galactic magnetic field, in turn, plays crucial roles in star formation, cosmic ray propagation, and the overall dynamics of interstellar gas. Without the magnetic pressure and support provided by these fields, molecular clouds would collapse too quickly to form stars efficiently. The delicate balance between gravity, thermal pressure, and magnetic pressure creates the conditions necessary for the slow, controlled collapse that leads to stellar birth. The cosmic rays accelerated in hypernova shockwaves represent another remarkable aspect of these explosions. These high-energy particles, primarily protons and heavier nuclei, are accelerated to velocities approaching the speed of light by the powerful magnetic fields present in the shock front. Once accelerated, they propagate throughout the galaxy, carrying energy and momentum across vast distances. The cosmic ray particles created in hypernovas don't just travel passively through space. They interact with the interstellar medium, ionizing atoms, heating gas clouds, and driving chemical reactions that would be impossible under normal conditions. They also interact with magnetic fields, creating synchrotron radiation that contributes to the radio emission we observe from our galaxy. Some cosmic ray particles achieve energy so extreme that they challenge our understanding of acceleration mechanisms. Individual protons can carry as much energy as a baseball traveling at 60 miles per hour, concentrated into a single atomic nucleus. These ultra-high energy cosmic rays may originate from the most energetic hypernovas, accelerated by shockwaves, moving at significant fractions of the speed of light. The detection of these extreme energy cosmic rays has opened new windows into hypernova physics. By studying their energy spectra, arrival directions, and composition, scientists can infer properties of their source regions that cannot be determined through electromagnetic observations alone. Each cosmic ray particle is like a messenger from the most violent regions of the universe, carrying information about conditions too extreme to study by any other means. The neutrinos produced in hypernova explosions deserve special attention because they provide unique insights into the explosion's core. Unlike photons, which can be absorbed and scattered by intervening material, neutrinos barely interact with matter at all. They escape from the explosion's center and travel across the universe virtually unimpeded, carrying pristine information about the nuclear processes occurring under the most extreme conditions. A single hypernova can produce more neutrinos in 10 seconds than our Sun will generate in its entire 10 billion year lifetime. These ghostly particles carry away enormous amounts of energy, perhaps 10% or more of the explosion's total energy output. The detection of even a few of these neutrinos from a nearby hypernova would provide unprecedented insights into stellar collapse, black hole formation, and the nuclear physics of matter under extreme conditions. The challenge lies in detecting these elusive particles. Neutrinos interact so weakly with matter that trillions pass through your body every second without leaving any trace. Detecting neutrinos from astronomical sources requires massive detectors, often containing thousands of tons of water or other target material, buried deep underground to shield them from cosmic ray backgrounds. Despite these challenges, neutrino astronomy is beginning to reveal new aspects of hypernova explosions. The IceCube Neutrino Observatory, built into a cubic kilometre of Antarctic ice, has detected high-energy neutrinos that may originate from jets in distant galaxies. Future detectors will be even more sensitive, potentially capable of detecting neutrinos from individual hypernova explosions across cosmological distances. The gravitational waves produced during hypernova explosions represent yet another messenger that carries information about these extreme events. As the stellar core collapses and forms a black hole, it creates ripples in space-time itself that propagate outward at the speed of light. These gravitational waves carry information about the collapse dynamics, the mass and spin of the newly formed black hole, and the asymmetries present during the explosion. Current gravitational wave detectors are sensitive primarily to the merger of compact objects like black holes and neutron stars. But future detectors may be capable of detecting the gravitational waves produced by stellar collapse and hypernova explosions. This would provide a completely new way of studying these events, revealing details about the collapse process that cannot be observed through any other means. The combination of electromagnetic observations, neutrino detections, cosmic ray measurements, and gravitational wave signals represents the future of hypernova astronomy. This multi-messenger approach allows scientists to study these explosions from multiple perspectives, creating a more complete picture than any single observational technique could provide. Each type of messenger arrives at Earth at different times and carries different information about the explosion. Gravitational waves and neutrinos travel at the speed of light and arrive first, carrying information about the collapse itself. Electromagnetic radiation follows, revealing the explosion's energy output and chemical composition. Cosmic rays arrive last, having been deflected by magnetic fields during their journey across the galaxy. By correlating these different signals, astronomers can reconstruct the timeline of hypernova explosions in unprecedented detail. They can determine when the core collapsed, when the jets broke through the stellar surface, when the shock wave began heating the surrounding gas, and when the explosion's products began mixing with the interstellar medium. This temporal reconstruction reveals the incredible complexity of hypernova explosions. What appears to be a single event is actually a sequence of interconnected processes occurring over vastly different timescales. The initial core collapse happens in milliseconds. The jet propagation through the star takes seconds to minutes. The shockwave expansion continues for years. The mixing of heavy elements with the interstellar medium persists for thousands of years. Each phase of this process operates according to different physical principles and creates different observational signatures. The core collapse is governed by general relativity and nuclear physics. The jet propagation involves magnetohydrodynamics and relativistic plasma physics. The shockwave expansion follows the laws of fluid dynamics and thermodynamics. The long-term mixing depends on turbulence theory and chemical evolution models. Understanding hypernovas therefore requires integrating knowledge from across the entire spectrum of physics, from quantum mechanics to general relativity, from nuclear physics to plasma dynamics. These explosions serve as natural laboratories, where all the fundamental forces of nature operate simultaneously under the most extreme conditions possible. The theoretical modeling of hypernova explosions pushes computational physics to its limits. Simulating the collapse of a stellar core and the formation of a black hole requires solving Einstein's field equations in 3 dimensions, while accounting for magnetic fields, rotation, and nuclear physics. The computational demands are so extreme that even the most powerful supercomputers can only model small portions of the explosion in full detail. Recent advances in computational techniques and computer hardware are beginning to make realistic hypernova simulations possible. These models are revealing new details about jet formation, shock propagation, and element mixing that cannot be observed directly. They're also making predictions about the gravitational wave and neutrino signals that should accompany these explosions, guiding the development of next-generation detectors. The comparison between theoretical models and observational data is driving rapid progress in our understanding of hypernova physics. Each new observation provides constraints on the models, while improved simulations suggest new observational tests. This iterative process is gradually building a comprehensive picture of these extreme events. But perhaps the most remarkable aspect of hypernova research is how it connects the smallest scales of physics to the larger structures in the universe. The quantum processes that govern nuclear reactions in stellar cores ultimately determine the chemical composition of entire galaxies. The relativistic effects that shape black hole formation influence the evolution of cosmic structure over billions of years. This connection between microscopic and macroscopic physics is one of the most beautiful aspects of modern astrophysics. By studying the most extreme events in the universe, we gain insights into fundamental physics that cannot be obtained through laboratory experiments. Hypernovas serve as cosmic laboratories where nature conducts experiments with energies and conditions that dwarf anything we can achieve on Earth. The implications extend far beyond pure science. Understanding hypernova explosions may be crucial for assessing the long-term habitability of our galaxy. These explosions can sterilize planets across hundreds of light years, but they also create and distribute the heavy elements necessary for life. The balance between destruction and creation determines whether galaxies can sustain life over cosmic timescales. Our location in the Milky Way appears to be fortuitously positioned in what astronomers call the galactic habitable zone. We're far enough from the galactic center to avoid frequent exposure to hypernova explosions, but close enough to benefit from the heavy element enrichment they provide. This cosmic real estate may be crucial for the long-term survival of complex life in our galaxy. The study of hypernovas in other galaxies reveals the diversity of these explosions and their effects on galactic evolution. Some galaxies show evidence of recent hypernova activity, with hot gas bubbles and enhanced heavy element abundances in their outskirts. Others appear quiescent, suggesting that their most massive stars have already exploded, or that star formation has slowed to rates too low to produce hypernovas. This diversity provides natural experiments in galactic evolution, allowing astronomers to study how different hypernova rates affect the chemical and structural evolution of galaxies. The results are helping to refine models of galaxy formation and evolution, revealing the crucial role that stellar feedback plays in shaping the universe we observe today. As we continue to unravel the mysteries of these cosmic monsters, we're also beginning to appreciate their role in the grand narrative of cosmic evolution. From the first stars in the early universe to the complex chemical environment of today, hypernovas have been key players in transforming simple hydrogen and helium into the rich tapestry of elements we observe around us. The story is far from over. Future observations will undoubtedly reveal new aspects of hypernova physics, new connections between stellar evolution and galactic dynamics, new insights into the processes that make life possible in our universe. Each discovery brings us closer to understanding our place in the cosmic story and our connection to the violent processes that created the elements of which we're made. In contemplating these ultimate expressions of stellar violence, we're reminded of the incredible journey that brought us into existence. The atoms in our bodies were forged in stellar cores and scattered by explosions that released more energy in seconds than our sun will produce in billions of years. We are, quite literally, the products of cosmic violence, temporary arrangements of stardust that have somehow learned to contemplate the explosions that created us. This perspective transforms our understanding of what it means to be human and our relationship to the universe around us. We are not separate from the cosmos, but intimately connected to its most extreme processes. The same physics that governs hypernova explosions also governs the chemistry of life, the formation of planets, and the evolution of consciousness itself. As we stand on the threshold of a new era in hypernova research, with gravitational wave detectors coming online and neutrino telescopes reaching new levels of sensitivity, we can look forward to discoveries that will further illuminate these cosmic beacons. Each new observation brings us closer to understanding the most powerful explosions in the universe and their role in creating the complex, element-rich cosmos we call home. The journey from stellar birth to hypernova explosion to the emergence of life represents one of the most remarkable transformations in the history of the universe. In studying these cosmic furnaces, we're really studying ourselves, tracing our origins back to the most violent events the cosmos has known since the Big Bang itself. The story becomes even more extraordinary when we consider the cosmic choreography that must align for hypernovas to fulfill their universe-shaping destiny. These aren't random explosions scattered haphazardly through space and time. They follow patterns, rhythms, and cycles that connect to the deepest structures of galactic evolution itself. Picture our Milky Way galaxy as it was 10 billion years ago, a young spiral still forming its distinctive arms, still gathering gas from the cosmic web that surrounds it. In those early epochs, star formation was more vigorous, more chaotic. Massive stars formed in greater numbers, lived their brief but brilliant lives, and died in explosions that lit up entire galactic regions with their fury. These ancient hypernovas didn't just create heavy elements. They sculpted the very architecture of our galaxy, carving out vast cavities in the interstellar medium, driving powerful winds that shape the spiral arms, and creating the complex network of hot and cold gas that we observe today. Each explosion was like a cosmic architect, redesigning the galactic landscape on scales that dwarf human comprehension. But here's what makes this story truly remarkable. The frequency of hypernova explosions has changed dramatically over cosmic time. In the early universe, when the first generation of stars was forming from pristine hydrogen and helium, these stellar giants were likely more common. Without heavy elements to cool their gas clouds, the first stars may have been true monsters, with masses reaching hundreds of times that of our Sun. When these primordial giants exploded as hypernovas, they began the great work of chemical enrichment that would eventually make our existence possible. Each explosion seeded space with the first heavy elements the universe had ever known, creating the building blocks for future generations of stars and planets. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it traces back to these ancient stellar deaths. As the universe aged and became more chemically enriched, the nature of star formation began to change. Heavy elements allowed gas clouds to cool more efficiently, fragmenting into smaller pieces and forming less massive stars. The era of the stellar giants gradually gave way to an epoch dominated by stars more similar to our Sun. Hypernovas became rarer, but their impact on galactic evolution remained profound. This cosmic evolution creates a fascinating paradox. The hypernovas that occurred billions of years ago made possible the formation of stars like our Sun and planets like Earth. But as the universe became more hospitable to life, it also became less capable of producing the massive stars that create hypernovas. We exist in a narrow window of cosmic time when the universe has been enriched enough to support complex chemistry, but hasn't yet evolved so far that hypernova explosions have become extinct. The timing of this cosmic evolution may be more than just coincidence. Some scientists have proposed that there's an optimal window for the emergence of complex life in the universe, a period when galaxies have been enriched with heavy elements but haven't yet exhausted their capacity for producing the massive stars that create those elements. We may be living in this cosmic sweet spot, a brief moment in the universe's history when conditions are just right for consciousness to emerge and contemplate its own origins. Consider the incredible precision required for this cosmic timing to work. If hypernovas had been too common in the early universe, their gamma-ray bursts might have sterilized entire galactic regions, preventing the formation of stable stellar systems. If they had been too rare, the universe might never have accumulated enough heavy elements to support rocky planet formation and complex chemistry. The actual rate of hypernova explosions appears to be perfectly calibrated to maximize both element production and habitability. They occur frequently enough to enrich the interstellar medium with heavy elements, but rarely enough that most star systems can evolve undisturbed for billions of years. This delicate balance may be one of the factors that makes our universe so remarkably suited for the emergence of life and intelligence. But the story of hypernovas extends far beyond our own galaxy. When astronomers peer deep into space, looking at galaxies billions of light years away, they're seeing the universe as it was in its youth, when hypernova explosions were more common and more energetic. These distant observations provide a window into the cosmic past, revealing how these stellar explosions shape the evolution of the early universe. The most distant hypernovas detected by astronomers occurred when the universe was less than 1 billion years old, during an epoch when the first galaxies were still forming and the cosmic web was still taking shape. These ancient explosions were often more energetic than their modern counterparts, releasing energies that exceeded anything we observe in the nearby universe. This evolution in hypernova properties over cosmic time reflects changes in the stellar populations of galaxies. Early stars, formed from gas that contained almost no heavy elements, could grow to enormous masses before encountering the physical limits that regulate stellar growth today. When these primordial giants collapsed, they created black holes more massive than typical modern hypernovas, launching jets with correspondingly greater energies. The jets from these ancient hypernovas may have played crucial roles in shaping the early universe. Their energy output was sufficient to heat and ionize gas across vast regions of space, contributing to the reionization epoch that transformed the cosmos from opaque to transparent. The heavy elements they scattered became incorporated into the first generation of metal-enriched stars, beginning the chemical evolution that would eventually lead to planetary systems capable of supporting life. Some of these ancient explosions may have been so energetic that their effects are still visible today. The largest structures in the universe, the cosmic web of galaxies and dark matter that spans billions of light years, may bear the imprint of hypernova explosions that occurred in the first billion years after the Big Bang. These cosmic fossils provide clues about the violent processes that shaped the universe during its formative epochs. The study of hypernova evolution over cosmic time has revealed fascinating connections between stellar physics and cosmology. As the universe expanded and cooled, the conditions for star formation changed in ways that directly affected the properties of the most massive stars. The decreasing density of the cosmic gas, the gradual enrichment with heavy elements, and the changing dynamics of galaxy formation all influenced how hypernovas evolved over billions of years. This cosmic perspective transforms our understanding of these explosions from isolated stellar events to integral components of universal evolution. Hypernovas aren't just the deaths of individual stars. They're participants in the grand transformation of the cosmos from a simple, element-poor state to the complex, chemically diverse universe we inhabit today. The energy budgets of hypernova explosions also reveal profound connections to the fundamental structure of space-time itself. The most energetic hypernovas release enough energy to create detectable distortions in the fabric of space and time, generating gravitational waves that carry information about the explosion across billions of light-years of cosmic distance. These gravitational wave signals represent a completely new way of studying hypernova explosions. Unlike electromagnetic radiation, which can be absorbed or scattered by intervening material, gravitational waves travel through the universe virtually unimpeded. They carry pristine information about the collapse dynamics, the formation of the central black hole, and the launch of the relativistic jets. Future gravitational wave detectors may be sensitive enough to detect hypernova explosions from across the observable universe, providing a cosmic census of these events that extends back to the earliest epochs of star formation. This gravitational wave archaeology will reveal how hypernova rates have changed over cosmic time and help us understand their role in universal evolution. The neutrino emissions from hypernovas offer yet another cosmic messenger that transcends the limitations of traditional astronomy. These ghostly particles, produced in the nuclear reactions that power the explosion, escape from the stellar core and travel across the universe at nearly the speed of light. Unlike photons, neutrinos barely interact with matter, allowing them to carry information from the explosion's heart to detectors on Earth. The neutrino signal from a hypernova contains information that cannot be obtained through any other observational technique. The energy spectrum of these particles reveals details about the nuclear processes occurring under extreme conditions. Their arrival time relative to the electromagnetic signal provides constraints on the explosion dynamics. Their flavor oscillations during the journey to Earth probe fundamental physics in ways that laboratory experiments cannot achieve. Detecting neutrinos from hypernova explosions requires some of the most sophisticated instruments ever built. Underground laboratories shield massive detectors from cosmic ray backgrounds while waiting for the rare interactions that signal the arrival of neutrinos from stellar explosions. Each detection is a triumph of experimental physics, revealing secrets about cosmic events that occurred millions or billions of years ago. The combination of gravitational waves, neutrinos, and electromagnetic radiation creates a multi-messenger approach to hypernova astronomy that is revolutionizing our understanding of these cosmic extremes. Each type of signal provides complementary information about different aspects of the explosion, creating a more complete picture than any single observational technique could provide. This multi-messenger revolution is revealing hypernova explosions to be even more complex and fascinating than previously imagined. The gravitational wave signal reveals the dynamics of core collapse and black hole formation. The neutrino emission probes the nuclear physics of matter under extreme conditions. The electromagnetic radiation traces the energy deposition in the stellar envelope and the interaction with the surrounding medium. By correlating these different signals, astronomers can reconstruct the timeline of hypernova explosions with unprecedented precision. They can determine when the core began its final collapse, when the central black hole formed, when the jets broke through the stellar surface, and when the explosion began interacting with the circumstellar environment. This temporal reconstruction reveals hypernova explosions to be incredibly dynamic events, with different physical processes dominating at different times and scales. The initial collapse happens in milliseconds, governed by general relativity and nuclear physics. The jet formation and propagation occurs over seconds to minutes, involving magnetohydrodynamics and plasma physics. The shockwave expansion continues for years, following the laws of fluid dynamics and radiative transfer. Each phase of this complex sequence creates its own observational signatures and provides insights into different aspects of fundamental physics. Hypernovas thus serve as natural laboratories where multiple branches of physics can be tested simultaneously under conditions that cannot be reproduced in terrestrial experiments. The magnetic field evolution during hypernova explosions represents one of the most extreme phenomena in the universe. As the stellar core collapses and forms a rapidly rotating black hole, magnetic field lines that were initially distributed throughout the star become concentrated and amplified by factors of trillions. The resulting field strengths approach the theoretical limits allowed by quantum mechanics. These ultra-strong magnetic fields don't just influence the explosion dynamics, they actually alter the structure of space-time itself, creating gravitomagnetic effects that have no analogue in everyday experience. The rotating magnetic field lines drag space-time along with them, creating frame-dragging effects that can be detected through their influence on the orbits of nearby matter. The magnetic field geometry becomes incredibly complex during the explosion, with field lines twisting, reconnecting, and forming structures that exist nowhere else in the universe. These magnetic configurations are unstable, constantly evolving as they seek lower energy states. The energy released during magnetic reconnection events can exceed the output of entire galaxies, contributing significantly to the explosion's total energy budget. Understanding these magnetic phenomena requires advances in both theoretical physics and computational modeling. The equations governing magnetohydrodynamics in strong gravity are among the most complex in all of physics, involving nonlinear couplings between electromagnetic fields, fluid dynamics, and general relativity. Solving these equations requires some of the most powerful supercomputers in the world. Recent computational advances are beginning to reveal the three-dimensional structure of hypernova magnetic fields in unprecedented detail. These simulations show that the magnetic field geometry is far more complex than previously imagined, with current sheets, magnetic islands, and turbulent cascade phenomena that operate on scales ranging from kilometers to light years. The particle acceleration mechanisms operating in these extreme magnetic environments are equally remarkable. Individual particles can be accelerated to energies that approach the theoretical maximum allowed by special relativity. The acceleration processes involve complex interactions between magnetic reconnection, shock waves, and plasma instabilities that are still not fully understood. Some of the cosmic ray particles detected at Earth may have been accelerated in hypernova explosions that occurred millions of years ago. These ultra-high energy particles carry information about the acceleration mechanisms and magnetic field structures present during the explosion. Each cosmic ray detection is like receiving a message from one of these ancient stellar deaths. The interaction between hypernova jets and the surrounding interstellar medium creates some of the most beautiful and complex structures in the universe, as the relativistic jets punch through the stellar envelope and emerge into space. They create bow shocks that heat the surrounding gas to temperatures exceeding 100 million degrees. These shock-heated regions emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. The emission is highly variable, flickering and flaring as instabilities develop in the shock front, and as the jet interacts with density variations in the surrounding medium. These variations provide insights into the jet structure and the properties of the circumstellar environment. The long-term evolution of hypernova remnants reveals the lasting impact of these explosions on their galactic environments. Years or decades after the initial outburst, the expanding shock waves continue to sweep up interstellar material, creating superbubbles that can remain visible for thousands of years. These structures serve as fossil records of ancient explosions, preserving information about hypernova properties long after the initial event has faded. Within these expanding bubbles, Complex mixing processes redistribute the heavy elements created in the explosion throughout volumes of space, hundreds of light years across. The mixing is driven by turbulent instabilities that develop at the interfaces between hot and cold gas. These instabilities create fractal structures with self-similar properties that extend across many orders of magnitude in scale. The chemical signatures of hypernova explosions become incorporated into new generations of stars that form from the enriched gas. These stellar populations carry the isotopic fingerprints of ancient explosions, allowing astronomers to trace the chemical evolution of galactic regions over billions of years. Each new star is like a time capsule, preserving information about the explosive events that enriched its birth environment. The connection between hypernova explosions and the formation of planetary systems is particularly intriguing. The dust grains created in these explosions serve as condensation nuclei for the formation of rocky planets. The specific isotopic ratios produced in hypernova nucleosynthesis can be detected in meteorites that formed in the early solar system, providing direct evidence for the role of these explosions in creating the materials from which Earth formed. Some researchers have proposed that hypernova explosions may have directly triggered the formation of our solar system. The shockwaves from a nearby explosion could have compressed the molecular cloud from which the Sun and planets formed, initiating the gravitational collapse that led to star formation. The heavy elements incorporated into the solar nebula would have come from the same explosion, creating a direct connection between our existence and one of these cosmic catastrophes. This possibility transforms our understanding of our place in the cosmic story. Rather than being passive beneficiaries of ancient stellar explosions, we may be the direct products of a specific hypernova that occurred in our galactic neighborhood 4.5 billion years ago. The atoms in our bodies, the rocky material of our planet, and the very processes that led to our solar system's formation may all trace back to a single moment of unimaginable violence. The search for evidence of this hypothetical trigger event has become an active area of research. Scientists are looking for isotopic anomalies in meteorites that might preserve the signature of a nearby hypernova explosion. They're studying the distribution of heavy elements in the local interstellar medium, searching for patterns that might reveal the location and timing of ancient explosions. The implications extend beyond our own origins to the broader question of how common planetary systems like ours might be throughout the universe. If hypernova explosions are necessary to trigger the formation of solar systems with rocky planets, then the frequency of these explosions becomes directly relevant to the search for life elsewhere in the cosmos. The role of hypernovas in galactic chemical evolution also has profound implications for the emergence of complexity throughout the universe. These explosions don't just create heavy elements. They create them in specific ratios that depend on the detailed physics of the explosion. Different types of hypernovas produce different element patterns, contributing to the rich chemical diversity we observe in galactic environments. The evolution of these element ratios over cosmic time traces the changing properties of hypernova explosions as the universe aged and evolved. Early hypernovas, formed from metal-poor gas, produced different element patterns than modern explosions from metal-enriched progenitors. This chemical archaeology allows astronomers to reconstruct the history of star formation and chemical enrichment across billions of years of cosmic evolution. Understanding these chemical evolution patterns is crucial for assessing the potential for life throughout the universe. Complex chemistry requires not just the presence of heavy elements, but specific ratios and abundances that enable the formation of complex molecules. The patterns produced by hypernova explosions may determine which galactic environments are capable of supporting the chemical processes necessary for life. As we contemplate the cosmic role of these stellar explosions, we begin to appreciate their function as agents of transformation in the universe's ongoing evolution. They serve as cosmic recycling centers, taking the nuclear waste products of stellar fusion and transforming them into the raw materials for new generations of stars and planets. They act as galactic gardeners, pruning overgrown stellar populations and sowing the seeds for future growth. The energy they inject into galactic environments regulates the pace of cosmic evolution, preventing galaxies from converting all their gas into stars too quickly, and ensuring that star formation can continue for billions of years. Without this regulation, the universe might have exhausted its fuel for star formation long ago, becoming a cold, dark place, devoid of the energy sources necessary for life. The magnetic fields they generate help maintain the galactic magnetic environment that protects stellar systems from harmful cosmic radiation. The cosmic rays they accelerate contribute to the ionization of interstellar gas, enabling chemical processes that would be impossible in purely neutral environments. The gravitational waves they produce carry energy across cosmic distances, contributing to the large-scale dynamics of space-time itself. In every aspect of their existence, hypernovas serve as connectors, linking the physics of individual stars to the evolution of entire galaxies, connecting the nuclear processes that create elements to the cosmic processes that distribute them throughout space, bridging the quantum world of atomic nuclei to the relativistic realm of black holes and jets. As we continue to study these remarkable phenomena, we're not just learning about stellar explosions. We're uncovering the fundamental principles that govern how complexity emerges from simplicity in our universe, how the death of individual stars can give birth to new worlds, and how violence and creation are inextricably linked in the cosmic dance that has brought us into existence. The story of hypernovas is ultimately the story of transformation itself, the remarkable process by which the universe has evolved from a simple soup of hydrogen and helium into the rich, complex, element-laden cosmos we inhabit today. In understanding these explosions, we understand something profound about the nature of change, growth, and evolution on the largest possible scales. And perhaps most remarkably, we understand something profound about ourselves, about our connection to these cosmic furnaces, and about our role as conscious observers in a universe that has evolved the capacity to study its own most extreme phenomena. We are the universe's way of understanding hypernovas, temporary arrangements of stardust that have learned to contemplate the explosions that created the very elements from which we're made. As you drift towards sleep, carried by the gentle rhythm of these cosmic revelations, let yourself marvel at the extraordinary journey that brought you to this moment. Every atom in your body, every molecule that makes you who you are, was forged in the heart of a dying star and scattered across the cosmos by explosions so powerful they defy human comprehension. The calcium strengthening your bones right now was created in temperatures exceeding billions of degrees. The iron flowing through your bloodstream was born in the final seconds of a stellar collapse. The oxygen filling your lungs with each breath emerged from nuclear furnaces that burned brighter than entire galaxies. You are not separate from these cosmic catastrophes. You are their living legacy, a walking testament to the universe's most violent, creative acts. Consider this remarkable truth as you settle deeper into contemplation. The gold in any jewelry you might wear contains atoms that were literally forged in a hypernova explosion, created in conditions so extreme that space and time themselves were warped beyond recognition. That precious metal traveled across light years of space for millions or billions of years before finding its way into the rocky debris that would become Earth, and eventually into the mines and streams where humans discovered it. But hypernovas have given us more than just the elements in our bodies. They've given us time itself, in a sense. The radioactive elements created in these explosions decay at known rates, providing cosmic clocks that allow us to measure the age of meteorites, date the formation of our solar system, and trace the chemical evolution of our galaxy. Some of these isotopes have half-lives measured in billions of years, meaning they're still decaying today, still releasing energy that was first stored in stellar death throes that occurred before our sun was even born. The heat warming Earth's interior right now comes partly from these ancient explosions. Uranium and thorium, created in hypernova furnaces billions of years ago, continue to decay in our planet's core, providing the energy that drives plate tectonics, maintains our magnetic field, and keeps our world geologically active. Without this radioactive heating, Earth might have become a frozen, dead world like Mars, unable to sustain the dynamic processes that make life possible. As you breathe in this moment, remember that the very air entering your lungs carries elements that have journeyed across the galaxy, the nitrogen that makes up most of our atmosphere, the trace gases that colour our sunsets, the water vapour that forms our clouds. All of it has been touched by the cosmic alchemy of stellar death and rebirth. You're not just breathing air, you're breathing the transformed remnants of ancient stars. The light reaching your eyes right now, whether from distant stars or the gentle glow of artificial illumination, travels at the same speed as the relativistic jets that emerge from hypernovas. That fundamental cosmic speed limit, the speed of light itself, connects the photons dancing across your retina to the most extreme physics in the universe. In a very real sense, the universe operates at the same tempo, whether it's powering your vision or launching jets of plasma across thousands of light years. The magnetic field protecting Earth from harmful cosmic radiation bears the influence of countless stellar explosions that have occurred throughout our galaxy's history. Each hypernova has contributed to the complex magnetic environment that permeates interstellar space, helping to maintain the protective magnetic bubble that shields our solar system from the worst effects of cosmic rays and solar storms. Even the cosmic rays themselves, those high-energy particles constantly raining down on Earth's atmosphere, may include messengers from hypernovas that exploded millions of years ago. Each cosmic ray detection is like receiving a postcard from an ancient stellar death, carrying information about magnetic fields and acceleration processes that operated under the most extreme conditions imaginable. The story becomes even more profound when we consider our role as conscious observers in this cosmic drama. Somehow, through processes we're still trying to understand, the universe has evolved from simple hydrogen and helium into arrangements of matter complex enough to contemplate their own origins. We are the cosmos becoming aware of itself, using brains built from stellar remnants to study the explosions that created those very elements. This perspective transforms our understanding of what it means to be human. We're not isolated biological systems struggling for survival on a small planet. We're expressions of cosmic evolution itself, temporary patterns that have emerged from 14 billion years of universal development. The same physical laws that govern hypernova explosions also govern the chemistry of life, the formation of memories, and the emergence of consciousness. In studying these cosmic furnaces, we're really studying ourselves, tracing our genealogy back to the most violent events the universe has known since the Big Bang. Every question we ask about stellar explosions is the cosmos inquiring into its own nature. Every discovery we make about element formation is the universe learning about its own creative processes. The beauty lies not just in the connections we've discovered, but in the fact that we can discover them at all. Against all odds, in a universe dominated by dark matter and dark energy, on a small rocky planet orbiting an ordinary star, arrangements of stardust have learned to decode the secrets of stellar death. We've built instruments sensitive enough to detect the afterglow of explosions that occurred billions of years ago. We've developed theories sophisticated enough to predict the behavior of matter under conditions more extreme than anything in our solar system. And we've done all of this using brains constructed from the very elements we're studying, powered by chemical reactions that depend on the precise properties of atoms forged in stellar cores. It's as if the universe has spent billions of years creating the tools necessary to understand itself, culminating in minds capable of appreciating both the violence and the beauty of cosmic evolution. As sleep begins to embrace you, carry with you this profound truth. You are not merely an observer of these cosmic phenomena. You are a participant in the ongoing story they tell. Every breath you take, every heartbeat that sustains you, every thought that flows through your consciousness is part of the universe's continuing evolution, from simplicity to complexity, from chaos to order, from stellar death to conscious life. The atoms that compose you have journeyed across space and time, surviving stellar explosions, planetary formation, and billions of years of evolution to come together in the remarkable arrangement that is you. You are a temporary coalescence of cosmic matter that has somehow achieved the extraordinary feat of self-awareness, a brief flowering of consciousness in the vast garden of existence. Tomorrow, the hypernovas will continue their cosmic dance, forging new elements in the hearts of dying stars, launching jets across galactic distances, and seeding space with the materials for future worlds. The universe will continue its patient work of transformation, creating complexity from chaos, beauty from violence, and meaning from the apparent randomness of quantum mechanics. As you drift into the realm of dreams, you can rest in the knowledge that you are part of something magnificent beyond measure. The same forces that create the most powerful explosions in the universe also created you. The same elements forged in stellar death flow through your veins and fire your neurons. The same physics that governs black hole formation also governs the beating of your heart. You are stardust dreaming of stars, cosmic dust that learned to wonder about the cosmos, a temporary arrangement of ancient atoms that somehow discovered how to contemplate infinity. In you, the universe has found a way to marvel at its own magnificent complexity, to stand in awe of its own creative power, and to find beauty in both the violent and gentle processes that shaped reality itself. Sweet dreams, fellow traveler in this cosmic story. Rest well knowing that you carry within yourself the legacy of the most powerful things in the universe, and that your very existence is proof of the remarkable creative potential that emerges from even the most catastrophic cosmic events. The hypernovas that lit up ancient skies live on in you, their energy transformed into consciousness, their violence transmuted into wonder, their destruction revealed as the ultimate act of cosmic creation. I wish you had fun on this amazing journey with me. I wish you a very good night. This is Boring Science signing off. Cheers.